Hi everyone. In the last scientific critical thinking video, we talked about this method of dimensional analysis, where if we have some system that depends on some set of physical parameters, we can identify different characteristic scales by finding combinations of those physical parameters that produce the corresponding dimensions that we're interested in. So if we want to find a characteristic length scale, well, look for the combination of the system's parameters that result in dimensions of length. If we want to find a characteristic time scale, find the combination that gives time. If we want to find an energy scale, find the combination that gives the same dimensions as energy, and so on. These combination of system parameters not only give us ways of estimating these various scales, but also give some key insights into how we expect these scales to change if we were to vary those systems' parameters. So given that all we're doing here is making sure that we're being consistent with what types of physical quantities we're talking about, and we're not equating masses and times or velocities and accelerations, just making sure that we're being consistent with these dimensions, it's actually a really powerful tool for being able to make these estimations. So in this video, we're going to apply this method specifically to the motion of a simple pendulum. We're going to make some predictions of how the pendulum's period should depend on its parameters using dimensional analysis. And then we're going to test those predictions by measuring the motions of a bunch of pendulums, and even having another way of measuring what is the value of g, the gravitational acceleration on the Earth. So let's jump right in. And let's start by asking, what do we mean when we're talking about a simple pendulum? So a simple pendulum is basically, I have a low mass string attached to a hanging mass. The string's a certain length, this is a certain mass, and we are assuming that we are on a planet with a certain value for the gravitational acceleration. So again, we've got our pendulum length, which we're just going to denote as script L. We've got the mass of this pendulum, and we're on a planet where the gravitational acceleration is little g. And we have the dimensions of these quantities. Length, mass, and dimensions of g are length per time squared. A couple of assumptions that we do make with this simple pendulum. We are assuming that the string is a low mass compared to this hanging mass. So the string has to be a negligibly small mass compared to what we have over here, which is going to be pretty much the case in what we have here. Also, when we're measuring the length, and this might be a little bit of source of potential measurement error, the length of the string is going to be measured from the fulcrum point to the center of mass of this hanging mass. So it's going to be maybe a little bit hard to measure exactly where that center of mass is, but that shouldn't be a significant source of error for this experiment. The other thing that we're going to be also assuming is that the size of this mass, not the value of the mass, but actually its physical length, is relatively small compared to the length of the pendulum itself. We could talk about physical pendulums, and maybe this will be a topic in a future video, saying, what if we have something where this string is not a negligible mass, or I have a bar or something that's swinging back and forth. Those are called physical pendulums. And the math gets a little bit more detailed with that. So for this one, we're just going to be sticking with this simple pendulum. So we want to ask, how does this pendulum, how long is it going to take to go through one full repetition of the motion? Because if I take this pendulum and just move it to the side a little bit and let it go, it's going to start swinging back and forth. And maybe I'm interested in what is the period of motion? How long does it take this thing to go back and forth once? So the period is defined as how long does it take to go through one full cycle of the motion. So if I pull this back a little bit, one full cycle would be a back and forth swing. One full back and forth repetition of the motion. So let's see if we can use dimensional analysis to identify what this time scale is going to be. So again, the parameters that describe our system is the length of the pendulum, that mass that's attached to the end of the pendulum, and this gravitational acceleration. And we want to find the combination of these terms that give us just time. Well, if we look at these parameters, the only term in here that even has dimensions of time is going to be the gravitational acceleration. Okay? But this is a length divided by a time squared. So if I just use g, I'm going to get time in the denominator for these dimensions, and that's not what we want. So instead of looking at the value of g, let's look at the dimensions of 1 over g. If I take 1 over some quantity, if I take the reciprocal of that quantity, I'm also going to take the reciprocal of the dimensions. So the dimensions of this would be time squared divided by length. Okay, just the inverse of the units of g. Okay. It would be nice to get rid of that length. So if I want to get rid of length in this denominator, I need some other length in the numerator. Well, we can multiply this by the length of the pendulum. So if I do the length of the pendulum divided by g, well, those units of length were, those dimensions were just length, and our 1 over g was time squared over the length. So notice that the length cancels out, and this just gives us units of time squared. But we don't want time squared for this period, we just want time. So let's take the square root of this quantity, and that will just give us units of time. So by using this dimensional analysis, again, the claim is that the period should be proportional to the square root of the length of the pendulum divided by the gravitational acceleration. Again, 9.8 meters per second squared. Again, if you're on the Earth. Now, there is a limit to what we can say with dimensional analysis alone. We can say that the period is proportional to that square root of length over g, but we don't know what the proportionality constant is. We do know that proportionality constant should be dimensionless because we've already got our dimensions of time here. But again, with dimensional analysis alone, we can't identify what that is. For the simple pendulum, we can actually apply Newton's laws to it and go through some of the calculus involved in looking at this back and forth simple harmonic motion. And using those methods, we can get the full details saying the period is equal to 2 pi times the square root of the length over g. But again, with dimensional analysis, we got a significant amount of this equation, saying how does this period depend on the length of the pendulum and depend on the gravitational acceleration. So again, with just looking at dimensional analysis alone, we got pretty far in this question. So the next thing is, what specific predictions does this make? So again, our claimed equation, the full details, is that the period should be equal to 2 pi divided by the square root of g multiplied by the square root of the length of that pendulum. And just for reasons that we're going to see a little bit later when we do the data analysis, we can write this in equivalently as 2 pi divided by the square root of g times the length of the pendulum to the power of 0.5. Taking the square root of a quantity is the same as taking that value to the power of 1/2. And with this equation, we can make a couple of predictions. Our first prediction is that the period of motion for this simple pendulum should be independent of the mass. Notice that when we did this dimensional analysis work, the mass of the pendulum didn't ever enter into the equations. So if that mass doesn't show up in the equations, then that is implying that this period of motion, how long it takes to oscillate back and forth, should not depend on the mass, and that's something that we can test out. We can also look at what sort of a relationship should there be between the period of motion and the pendulum length. So if I were to make a graph of the pendulum length versus the period of the motion, then what we should get, according to this model, is that we should get this matching up with a power fit. Okay, so this was the equation for our power fit. I mentioned these different kinds of fit and how to apply this in a previous video. But in this particular case, when we start graphing this data, we should get this particular kind of fit that we call a power fit. And we can take this best fit equation, when we actually take our data, graph this data, look at what the best fit is. We can take this power fit and match it up with the period to, again, make some very specific predictions. So the idea is that our data, let me make a bit more room over here. Our data should be in the form y equals some constant, capital A, times whatever's on the horizontal axis to the power of some other constant b. Our claimed equation, so this is our data, and our claimed equation is that the period is equal to 2 pi divided by the square root of g times the length of the pendulum to the power of 0.5. Okay. So what we want to do is compare what kind of a fit we get from our data. We haven't taken the data yet, we're going to be doing that shortly, but compare what mathematical pattern we get from the data and compare that with our claimed equation. In this one, the kind of graph that we're going to make, we're going to put period on the vertical axis. So the thing that we put on the vertical axis, that matches up with period. The thing we're going to put on the horizontal axis, that's going to match up with the length of the pendulum. So if this claim is correct, again, this particular relationship between the period and the length of the pendulum involving this square root, again, that we got from dimensional analysis. If this is correct, then the value we get for this exponent b should be 0.5. And the value that we get for this coefficient in front, this capital A, that should be 2 pi divided by the square root of g. And if you plug that in, saying g is 9.8 meters per second squared, 2 pi divided by the square root of 9.8 gives us around 2.01. It's like 2.007 something continuing on, but again, pretty close to 0.201. So we're making these very, very specific predictions based on the results that we got from both the dimensional analysis, and the only thing that adding in the full Newton's laws detail got us was this factor of 2 pi. So those are our predictions. Let's start building some pendulums and start taking some data. So we've got a pendulum, a low mass string, a small mass attached to the end of it, and when we measure the length of this thing, we are going to measure the length from the fulcrum point to around the middle of the mass. A couple of things before we actually start taking data though. When we're timing how long does it take to go back and forth through one period of the motion, if I try to do 3, 2, 1, start, stop, that really short time is going to be hard to measure accurately with a stopwatch. So instead of measuring just one back and forth cycle, we're going to look at how long does it take to go through 10 cycles. So when I release it, we're going to count up 1, 2, going through 10 full cycles to get an accurate measurement for what this period is. And then if I know the time for 10 cycles, well, I just divide that by 10, the number of cycles, to get how long does it take to go through one cycle. And that should give us a much more accurate result. One other thing that I want to mention is that for these simple pendulums, as long as the angle that we're pulling at initially is relatively small, I'm not pulling it like, all the way up to 90 degrees or something like that. As long as this angle is relatively small, the period won't be affected by me pulling back a different amount. Let's actually try that as our quick check. So this mass right here, this is a 50 gram mass, so that mass is going to be 0.05 kilograms. The length of this pendulum, if I put this to the, again, approximately the center of this mass, this isn't going to be perfect, but hopefully it'll be close enough. So from the center of that mass to here, that's 10, 20, 30, 40, 50, 67 centimeters, so 0.67 meters. And let's do two cases with this one. One with a very small amplitude motion, so just going back and forth a little bit. I'll try to make it a little bit larger than that. And then one with a somewhat larger amplitude motion to see, does that affect the period of the motion as long as we're, again, not pulling this out to 90 degrees. So, again, you can do this experiment yourself. This is a very much an experiment that you can do with minimal equipment, a stopwatch, a ruler, and some setup for this pendulum. But let's try small amplitude motion. Again, we're waiting through 10 full cycles of the motion, starting in 3, 2, 1, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. Okay, so I got 16.19 seconds for 10 cycles. So that means the period is 1.62 approximately, 1.62 seconds if we round that to 3 significant figures. Again, my ability to start and stop the timer exactly right is going to be a little bit off, but if it's a little bit off for 10 cycles, when I divide by 10, that small error is going to get much smaller for this, 10 times smaller for this. So this is going to be a pretty accurate value of that period. So that was with a small amplitude motion. Let's reset and do this with a larger amplitude motion. As long as I don't hit the side over here, let me move my camera a little bit more so you can see this larger amplitude motion. As long as I don't hit the beam over here, we should be okay. So let's do this again, 10 cycles starting in 3, 2, 1, start. 1, 2, again this is a larger motion, 3, 4, 5, 6, 7, 8, 9, stop. Okay. That time I got 16.27 seconds. So that's in really close agreement. Again, this could be plus or minus maybe 0.2 seconds if I'm, say, off by 1/10 of a second for both the start and the stop. Again, this one being 16.27 seconds, that's going to be within, our uncertainty measurement. Having that larger amplitude motion did not seem to affect the motion of this pendulum. So I'm going to switch out this 50 gram mass for a 200 gram mass. Notice that this is a little bit longer. This mass is a little bit longer, so I'm going to shorten the string slightly so that, again, the distance to the center of this mass is still 0.67 centimeters. Sorry, 0.67 meters. So let me switch that up. Okay, so let's check this length, see if, again, to the center of the mass. Yeah, right around 0.67 meters. So again, we've changed this to a 0.2 kilogram mass. Length is still 0.67 meters. And let's reset. And again, it doesn't matter. We've identified that it doesn't really matter how much I pull this to the side. I'm still going to go with a fairly small amplitude oscillation. So let's start this trial in 3, 2, 1, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. I got 16.14. So the period would be 1.61 approximately for that. So again, I changed the mass by a factor of 4. Doesn't seem to have affected the period very much at all. So again, so far we seem to be getting this period is independent of the mass, but let's try a larger mass. I'm going to switch this one now out for a 500 gram mass. Again, this one's longer, so I'm going to have to shorten this pendulum again. All right, that looks pretty good for, again, 67 centimeters. So again, 0.67 meters. Now our mass is half a kilogram. And we're going to do exactly the same test again. So let's reset. I'm going to pull this a little bit to the side. And 3, 2, 1, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. Yeah, I did not expect to get it that accurate. So 16.19. So again, these times for 10 cycles, again, just with human reaction times, I'd expect those to be accurate to within around, 0.1 or 0.2 seconds. But even though we're changing the mass from 50 grams to 500 grams, a factor of 10 change, it did not seem to affect the amount of time it takes to go through 10 cycles. It did not affect the period of the motion. So this first prediction that we had, that the period is independent of the mass, that one seems to hold true. Okay. So what we're going to do next is say, what if I'm changing the length? The mass doesn't seem to affect the period of the pendulum's oscillation, as we were predicting, but we're saying the length should affect the period of motion. In fact, if I increase this length, the period should increase as well. So we're going to try a bunch of short pendulums, a bunch of medium and longer pendulums, and let's start taking some of that data. So for this next part, we're going to just rapid fire our way through a bunch of different pendulums and measure how does the period of the pendulum depend on the length. We're going to start with this as our shortest one, and I don't really want to use a pendulum shorter than this for two reasons. First, if I have a shorter pendulum, it's going to take less time for that to go back and forth. So if I'm measuring shorter times, I don't want my human reaction time to be a significant source of error in this. So it's better to measure longer times if that's possible. Also, for this simple pendulum model, we said that the size of the mass itself, the length of that mass itself, should be fairly small compared with the length of the string. And this is about as far as I want to push that particular assumption. So this is going to be our smallest pendulum. I'm going to use 50 grams for all of these cases. And for this one, looks like the length of that pendulum is 12 centimeters, so 0.12 meters. So again, this is going to be 0.05 kilograms, and this is 0.12 meters. And let's do the same thing as before. We're going to measure the time for 10 cycles. So pull this back, and 3, 2, 1, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. Okay, so I got 6.83 for that. Again, it's a much shorter time than we had before. And if that is the time for 10 cycles, I would divide this number by 10 to figure out the time for one cycle. So this would be around 0.683 seconds for one cycle with this length. Okay. So I'm going to switch up the length, and let's do another trial. Okay, so I increased the length of the string a little bit, and now the length of the pendulum, again, trying to get as close as I can to the center of that mass to here. Oh, that looks like that's 24 centimeters. Didn't actually try that, I was just adjusting that. So that is 0.24 meters. We're still using the 0.505 kilogram mass. And let's measure the motion. So same setup as last time, move it to the side, and we're going to start the timer in 3, 2, 1, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. Okay, I got 9.57 seconds for that. So the period would be 0.957. And again, let's change the pendulum again. And again, I encourage people to try this on their own. Make sure I'm not, faking data in any way. Again, you can make these simple pendulums. The mass, we already found that the mass doesn't matter. So get some string, attach some mass to it, and try to time this yourself. But let's get another pendulum length. Okay, so made some adjustments, and now the pendulum length looks like it is just over 37 centimeters. Let's call it 37.5 centimeters. So again, the mass is still 50 grams. This is 0.375. Double check that measurement. Yeah, I'd say that's a good approximation. And let's run the data. So same experiment, pull to the side, and 3, 2, 1, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. I got 12.05. So the time for, that would be the time for 10 cycles. The time for 1 cycle would be 1.205 seconds. Let's change the length again. Okay, let's try this one. So what length are we getting for this? This seems to be around, if I line that up on the bottom, this seems to be around 53 centimeters. So 0.53 meters, same mass. Let's measure the time. So reset, move to the side, and 3, 2, 1, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. I got 14.38. So that would be, for 1 cycle, that would be 1.438. We've already got a 67 centimeter one, so I'm going to try to make a longer pendulum than that. So let's reset this. Sure, let's go with this one. So this pendulum, if I set this up, so from there to here, it's 81 centimeters. So 81 centimeters for this next pendulum. And 0.05 is still the mass. And let's reset and measure the period. So releasing in 3, 2, 1, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. Okay, I got 17.92. So 1.792 for 1 cycle. And let's see if I can get one pendulum that's over a meter. I'm going to have to adjust my camera for this, so we'll make this one work still. Okay, so this pendulum is more than a meter long, so I've got my 2 meter long ruler here. So putting that right to the end, right to the middle of the mass, right there, and comparing that on this end, this is 1 meter, 1.07 meters. So let's record that one. Again, still 0.05 kilograms, 1.07 meters. And I will aim the camera down so you can actually see this thing moving back and forth. I think this will be our last one, because if anyone wants to try to, do a longer pendulum and see if the results are still matching up with what we've talked about here, throw a comment in and talk about that. So again, this is the 1.07 meter long pendulum. Move this back a bit, and we'll start in 3, 2, 1, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. Okay, I got 20.45 seconds for that, so 20.45. So the time for 1 cycle would be 2.045. And now we've got data for 7 different pendulums, ranging from 12 centimeters long to 1.07 meters long. Okay. So this should give us some good data to work with. So let's see how we can analyze the data, make our period versus pendulum length graph, and see if we actually get this fit for the power fit. So with this data that we've gathered, again, there are a few sources of error. Since the mass that we were primarily using, it does have a little bit of an extent. I might have been off by maybe a ½ centimeter in measuring the lengths of these. So some of those that could be, a few percent, especially for these smaller length pendulums. And just with, human reaction times, the time for 10 cycles might have been off by, 1 or 2 tenths of a second, which, again, for some of these would correspond to, maybe a couple percent off. So, again, those are the kind of order of the errors that we expect to see, around a few percent at most for this. But let's see what happens when we graph this data. So, again, the kind of graph that we want is we want to put the period of the motion on the vertical axis for this graph, and we want to put the length of the pendulum on the horizontal axis. So I went ahead and graphed this data. So again, these are the lengths that we used, and these are the corresponding periods for one cycle. Again, these lengths are in meters, and these periods are in seconds. And this is the scatter plot that we get from that data. Now, you'll notice that these data points, it looks a little bit linear, but if you actually try to put a linear fit on here, you'll notice that there is a little bit of a curve to this. Okay? So the linear fit isn't the best kind of fit for this particular data that we have. What we want to use instead is, again, this power fit. And we said that for this power fit, the, again, period is on the vertical axis, the length of the pendulum is on the horizontal axis, and with that matchup, we should get that the this exponent should be around 0.5. It would be exactly 0.5 if we did the experiment perfectly, but again, there's no such thing as perfect data. And the value for the coefficient in front should be 2.01. So if I apply a power fit to this data, well, let's try the fit. Hit OK. And let's see what we got. So again, this data is making this power fit pattern, and notice that that best fit curve matches the data very, very well. We've got a correlation of 0.9999, so really good fit for this data. And let's look at some of these values. We were predicting that based on this model and based on what we got from dimensional analysis, we found that this exponent for this graph should be 0.5. We got 0.50, let's round that up to 6. So we'll even be a little pessimistic on this and say it's 0.506. So again, we were expecting 0.505, we got 0.506, and when we do the percent difference, the percent error on what we got compared to what we were expecting to get, looks like we've got a match to within, just over 1%. In post, I'll actually, show that calculation on there, so it'll be somewhere on the screen right now, that for that exponent, we got within, 2% of the expected value. Okay. What about this coefficient in front, this capital A value? Well, if the prediction was that we should get 2 pi over the square root of g, which is around 2.007, we'll round that to 2.01, we got 1.98 compared to 2.01. Looks like that's around 1.5% off. Again, a really close match with that data. So again, this prediction that we were making based on, again, the dimensional analysis, where we found that, the period should be related to the square root of the length of the pendulum divided by g, that matched with predictions. And that prediction, that dimensional analysis, was based on these dimensions for these units, saying the length of the pendulum is obviously a length, the mass is obviously a mass, and this gravitational acceleration is a length divided by a time squared. If we didn't have that time squared in there, we would have gotten a different prediction for how this period of the motion should relate to, again, both the length of the pendulum and this value of g. But using that value of g in meters per second squared, saying those are the units for meters for little g, meters per second squared, that matched our data. But again, maybe this kind of model of saying, oh, I'm going to use all of my data together and get this particular pattern and find out exactly what kind of mathematical pattern we get and kind of comparing that to our prediction. Maybe you think, again, I'm being, I'm hiding something here. So let's have another method for actually using each of these data points. We're going to use each one individually and try to measure the value of little g. Okay? Because again, if this period for any pendulum is 2 pi times the square root of the length divided by the square root of g, if I have any pendulum and I know the length and I measure the period, I can use that to get a measurement of little g. Doesn't have to be any particular pendulum, as long as it's this simple pendulum, a small mass attached to a low mass string of length L. Then I can rearrange it. So let's say I take this equation, I'm going to multiply both sides by the square root of g and divide both sides by the period. Quick little rearrangement there. And then I'm going to square both sides. When we square both sides, we have to square each of the terms on this right side of the equation. So the 2 gets squared to 4, pi gets turned into pi squared, square root of L, when I square that, I just get the length of the pendulum, and divide by the period, I'm now dividing by period squared. This prediction for how we can measure the value of g, it's 4 times pi squared, which is unitless, it doesn't have dimensions, times the length of that pendulum in meters, divided by the period in seconds, and we square that value. So let's see what we get when we actually take this. So I'm going to use this data. Let me kind of move my screen around. Let's get a prediction for the value of g. And here, I'm going to highlight all these, so hopefully they will all show up as larger sizes on there. Okay. So the way that we can calculate this, we can get the computer to calculate this for us. We're going to say this is going to be equal to 4 times the computer's value of pi squared times, we want the length of the pendulum, divided by that time squared. Okay. Now again, when we look at each individual data point, it's probably going to be less accurate than what we used for the data as a whole, especially when we have some of these shorter pendulums. Okay? But let's see what we get. We were expecting to get 9.8. For this one, I got 10.1. But maybe that one was a fluke. I can repeat this calculation for each one of these. And notice, looks like I'm getting a little bit of overestimate, so maybe the point that I was picking as the very center was a little bit off, or maybe I was, always a little bit late with my timing. Again, there could be a couple of things throwing this off, but they're all pretty close to 9.8. In fact, let's calculate the percent difference. So we're going to do the percent error for each of these. I'll highlight all these and make sure that we can see the results for this one as well. And again, the percent error is the difference between my experimental value and the real value divided by the accepted value for g of 9.8 meters per second squared, and then multiplied by 100 to write that out as a percentage. So I'm going to calculate this by doing that value minus 9.8. And okay, so you can see it, that I'm typing in the right thing here. Divided by 9.8 for our true value. And then we have to multiply this by 100 to convert this to a percentage. So this first value was off by less than 3%. And when we look at the other ones, our worst case was, again, for one of the shorter pendulums. When we did some of the longer pendulums, we're mostly around like 2 or 3% off. But for all of these, we're all, at worst, 5.5% off of the true value. So again, this is another method that we can use to measure the value of g, and the way that we got this value of g was by taking 4 times pi squared, again, no units associated with that, times the length of the pendulum divided by the period in seconds squared. We are taking that period in seconds and we are squaring that value. The value of g is measured in meters per second squared. Again, in the previous video, we measured this using projectiles. And again, got those units of meters per second squared. In this one, we're using pendulums. In all of these cases, the value for g that we get is in meters per second squared. Sorry that I'm putting that much emphasis on this part. So again, this is an experiment that you can, do at home. Don't believe me, don't believe my data. Try it yourself and see if you can set up a pendulum, measure the length, measure what the period of the motion is, and try calculating the value of g yourself using this method and see if you get something that's relatively close to 9.8 meters per second squared. So that's going to be it for this video. As always, if you have questions, then throw them into the comment section. I try to answer those. Be kind and courteous when you're responding to other comments, and see you all in the next video.